Good afternoon to all. I, Sumandeep Kaur, Research Scholar, Department of Physics, Maharaja Ranjit Singh, Punjab Technical University, Bathinda. Welcome you all for the third session of Day 4, ATAL FDP on novel materials and their applications. This session being addressed by Dr. Jasbir Singh Hundal. Professor Jasbir Singh Hundal is working as professor and HOD in the Department of Physics, Maharaja Ranjit Singh, Punjab Technical University, Bathinda. Dr. Hundal completed his MSc Physics in 1984 and MPhil in 1986 from Guru Nanak Dev University, Amritsar. Dr. Jasbir Singh Hundal earned his PhD degree from IIT Roorkee and postdoctorate from Material Research Institute, Pennsylvania State University, USA. Research interests of Dr. Hundal are piezo and pyroelectric polymers, ferroelectric polymers and composites, and multi-fried composite materials. Dr. Hundal has research lab experience in dielectric measurements, ferroelectric measurements, and various sample preparation methods. Dr. Hundal supervised 5 PhD and more than 9 MSc students. He has published more than 80 research papers and 15 conference papers. Dr. Hundal served on various administrative positions as Dean Academic Affairs of Gyani Jail Singh College of Engineering and Technology, Bathinda, as Campus Director, Gyani Jail Singh College of Engineering and Technology, as a Registrar, Maharaja Ranjit Singh Punjab Technical University, Bathinda, and Dean Research and Development, Maharaja Ranjit Singh Punjab Technical University, Bathinda. Now I invite Professor Jasbir Singh Hundal to start his informative talk on piezo, pyro, and ferroelectricity in cyanopolymers. Over to you, sir.
Okay. First of all, good afternoon, everybody. Thank you very much, Suman, and thank you very much, Dr. Satnam Singh. In the beginning, I would like to thank AICT for granting us faculty development program on novel materials and their applications. And it wouldn't have been possible to organize the function or get the funding without the help of our Honorable Vice Chancellor, Dr. Bhuta Singh Sidhu. And this program is from minute to minute, it is being coordinated by Dr. Satnam Singh and supported by his research scholars. Thank you so much for introducing me. Probably I didn't need that long introduction here. Okay, and as informed by Suman, I shall be speaking on mainly ferroelectric materials, and I'll be talking mainly of piezo, pyro, and ferroelectric properties that we shall be that we measure in case of cyanopolymers, right? And I'll just share the screen here, then we will be able to. Okay, because essential thing for a polymer to be ferroelectric or say piezoelectric or pyroelectric is that it has to be a insulating material, right? It has to be a perfect dielectric. It shouldn't have any conducting properties. Okay. So we always think that probably polymers are only insulating. But interestingly, we have polymers which are highly conducting also. Okay, we have the polymers which have very high conductivity. It is of the order of superconductors only. They are good superconductors also. So when we talk of polymers, they lie in a very wide range. Their conductivity lies from highly insulating to highly conducting materials. In fact, at Roorkee, we also worked on polymer-based diodes, and that was basically we were working on polyvinyl alcohol, so that's also a type of conducting polymer. So we doped with P-type, N-type, and yes, we were able to get a rectification factor of around, I'd say, 10 times, right? Yeah. I hope you can see the screen now.
Yes.
Namse, can you? Are you able to see the screen?
Yes, sir.
Yes, sir. Yes, sir. And this
Slide भी नजर आ रही है? Are you able to?
and visible as properly visible.
So these are the this is the topic I am going to speak on. They are basically a class of ferroelectric materials. Shall be talking of piezo, pyro, and ferroelectricity, especially in sinopolymers, right? So that is the topic which I am going to speak on today. Now, as I was discussing that polymers can have different kinds of properties, like, okay, and based on the different properties, they have different types of applications. For example, these can, if we have ferroelectric or dielectric materials having very large dielectric constants, then they find applications in capacitors. But if the materials have large piezoelectric constants, then they can be used as pressure sensing devices, sonar detectors, strain sensors, actuators, coin counters, and different types of piezoelectric applications. And then we have some pyroelectricity. If they have pyroelectricity with them, then they can be used for infrared imaging. They can be used as IR detectors. So there are huge number of applications. Even I've read somewhere that they have been used for in car parking also, because engine of a car, when it's very hot, that emits infrared radiations. Okay, so sensors can actually tell you which place the parking is vacant. So it can automatically help you in parking the vehicle. So first one was piezoelectric, that we were talking of property of piezoelectricity and their applications, piezoelectricity and their applications. Now, if the materials exhibit hysteresis loop, they have two stable states, and one state can be switched to another one. And they have DE hysteresis kind of clocks. Then obviously they can be used in memories also. They can be used in random access memory. They can be used in other kind of applications also. Okay, and if they have property, they have large non-linear polarizability that can be used for optical memory displays. So polymers are literally a new field. I mean, to work on. Of course, work started in 1980s or 70s, but applications are huge, really huge. Okay. Now we come to what basically piezoelectricity. It is something like when a particular crystal is pressed, okay, when it is pressed, then it is found that sometimes the same phase, sometimes the other two phases, they develop some kind of electrical charges. Okay, so whenever a crystal is subjected to mechanical stress, or in other words, is under mechanical strain, then the other pair of phases develop equal and opposite charges. And if the direction of instead of tension, if instead of pressing, if we put the crystal under tension, then polarity of the field developed that gets reversed, right? So this piezoelectricity was first discovered in quartz crystal by Curie, Jacques and Pierre Curie, and now it has been because since it can be used for making sensors, right? Pressure sensing, temperature sensing, memories. So that's the reason why this field is of a lot of interest, right? So that's the huge reason why we are taking a lot of interest into that. Okay, and ceramic materials had always been used, like we talked of quartz. We have barium titanate, we have ADP, we have KDP. Then we have pure polymers, then we have composite materials. So we shall be talking of, these are all different stages of development in the ferroelectric materials, how the progress took place, right? So as I just explained that quartz was first known naturally existing piezoelectric crystal. So piezoelectricity was studied in quartz first. So it was discovered there. So for that purpose in A, I have shown two pictures. Okay, if you look at these two things, you find that, yes, first one essential thing here is that for a material to be piezoelectric, the material has to be non-central symmetric. Quartz crystal, if it is not stressed in unstressed position, have uh, they have no dipole. It doesn't have any dipole moment because centers of gravities of say positive and negative charges, they are just coinciding with each other. So for a dipole moment to exist, you must have equal and opposite charges. They are supposed to be apart. They have to be some distance apart. Then only you can have a dipole moment. So essential thing for materials to have to exhibit say piezoelectricity or pyroelectricity or ferroelectricity is that they should have some dipole moment, or if they have no dipole moment under unstressed conditions, then under stressed conditions at least they should have a dipole moment. So this is what is happening in stressed condition of quartz as shown in figure A. All right. So here what we find here is uh, these negative ions. The positive ions they have moved slightly upward, and the positive ions have moved down. Okay, this would be better clear in the next picture, which I'm going to next slide when I show. Now here we have again another crystal that doesn't have any that has center of symmetry. It is not non-central symmetric, so dipole moment can never be there. So in the section B, we find a crystal whether it is unstressed or stressed, it gives rise to no polarization. Whereas in case of A picture, when the crystal is unstressed, polarization is zero, but when it is stressed, P is there. You can see the direction of P. So essential thing for it to have is to have non-central symmetric crystals. So that's a very important thing to have. Okay, this is better explained here. Now, again, this is a quartz crystal, right? And this lower two positive ions. So under normal conditions, the centers of positive ions and negative ions, they seem to coincide. Okay, the angle is say theta. So this is under normal state when there is no dipole moment. Now, when this crystal is stressed along x-axis, what happens? This theta increases. So when this theta increases, in other words, what we are saying is that this dotted triangle, that the triangle made by these dashed positions, it appears to be moving up. Okay, as compared to the negative charges. So the upper surface is bound to get positively charged, and lower surface will get negatively charged. If, on the other hand, if you press the crystal along, the crystal is compressed along x-axis, in that case, theta will decrease, right? With the decrease in theta, it will appear as if this triangle of positive ions, it moves in the downward direction, right? So the lower surface will develop positive charge, and comparatively the upper surface will develop a negative charge. So you can see that when the crystal was under tension, upper surface was positively charged, lower surface was negatively charged, and it is exactly opposite when crystal is compressed. So that is essential property of a piezoelectric crystal. Okay, so when this quartz crystal is under stress, when it is either elongated or when it is compressed, then only it is in that particular phase of piezoelectric crystals, right? So this is in case of, so this is essential thing for a material to be piezoelectric, right? Now in this case, so there is sometimes there is a confusion about piezoelectricity and electrosection effect. Now in this case, whether you press the crystal along x-axis, you compress it, or you stretch it, right? In either case, the non-central symmetry will not arise in this crystal at all, right? Whether you apply the tension along x-axis or you compress the crystal along x-axis, still centrosymmetricity will not be lost. Okay, when centrosymmetry is not lost, that means dipole moment is not created, right? So in such cases, there is no polarization produced as such. Okay, and so this is basically electrostatic effect. And essential thing here is that we shall be talking of later when we talk of states and other, that polarization will be proportional to the Pauling field that we shall be talking of, the field you apply to create polarization. Okay. So when we talk of different kinds of materials that can exhibit this piezo, pyro, and ferroelectricity, we can have single crystalline solids, as we talked of quartz. Okay, but as I told you earlier, that essential condition is lack of centrosymmetry. That's very important. So that is in case of single crystals. You can have quartz, you can have some other crystals as well. And they are being used. I mean, you must have seen quartz clocks or watches. Everywhere it is being used, right? Okay. Then you can also have polycrystalline ceramics. Now, these polycrystalline ceramics, like you have barium titanate, you may have lead zirconium titanate or barium calcium zirconium titanate. So all the crystals are ceramics. So first one are single crystal materials like quartz we talked of, or we can have polycrystalline ceramics like barium titanate, lead zirconium titanate, or BCZT. So these are pure materials which we are talking of, right? And another type of new entrants in case of piezoelectric, ferroelectric materials are ferroelectric polymers, as I told you, right? And PVDF is the one that has been thoroughly researched upon. Now, this particular polymer, have found huge number of applications. I'm just going to name a few at the end of the lecture, but actually PVDF is hugely. I mean, there are I have read 2-3 books where the applications of this particular material are made. Okay, so in addition to PVDF, we may have PVF, that is polyvinyl chloride. You can have PVC, polyvinyl chloride, or you can have polyamide, that is nylon basically. Or you can have cyanopolymers like polyacrylonitrile. You can have polyvinylidene cyanide or polyvinyl cyanide, right? Or you can, so there can be different types of polymers. Now, ceramics, essential thing is that ceramics are quite brittle. And if you try to make sensors out of them, then you can't make large area sensors. So these ferroelectric polymers have an advantage. They are flexible. You can tailor make a material for a particular kind of application. You can even choose the shape. Okay, you want to have it in a conical form, you can have that. You want to have it in film form, you can have that, right? If you want to make a slight curvical structure, then you can even do that, right? With the polymers, but otherwise, with ceramics, making of large area sensors is simply not possible. Okay. Now, in case if we compare the piezoelectric coefficient and other things, it is slightly less in polymers as compared to ceramics. There is no doubt in that. But polymers have their own advantages. Like PVDF we are talking of is also found to be non-toxic and biocompatible. That means it can be used in transplants within a body, right? Human body. They are biocompatible. Same with PVDCN. So these 2-3 polymers have been widely used for biomedical application, which we shall be talking about later. Okay, when we talk of polymers, they essentially have long chains, and it has been found that stretching a polymer film or annealing it or polling it or doping it with copolymer can also enhance its piezoelectric, ferroelectric, and other properties. We shall be talking of how this thing is done, say in case of cyanopolymer. This is what we are going to talk of in detail at the later end, right? These are some of the polymers which we talked of, and next thing that happened after we talked of pure ceramic materials, pure crystals, or pure polymers, uh, the choice was to either make copolymers or make ceramic polymer composites. So a lot of people are these days are working on ceramic polymer composites. Even I have one or two students who are working on polymers, ceramic composites like PVDF and PCCRT. One so is already on the verge of completing his work, right? So interesting thing is that the high uh, ferroelectric, good ferroelectric polymers or ferroelectric properties of ceramics uh, mixed with the polymer used as matrix can also help us in a good way. So that is so again composite materials which we talk about. So actually most of the things are composites, right? They are not pure. So the ceramic polymer composites are also very helpful. So, as I told you, this is brief history. Like we had it in quartz, rochelle salt, barium titanate, lithium niobate, and so on and so forth. So this is tracking down the history, and you can find that if you talk of PVDF, BCZT, or other mixtures, uh, they are not very old. Kind of the people are still working on those, right? Okay, so we had talked of slightly of piezoelectricity and now ferroelectricity. This is something very basic that material needs to have spontaneous polarization. That is one essential condition. And it should have two stable states. And the direction of spontaneous polarization should be reversible. That is when you apply a field in a particular direction, you may attain a saturation polarization. Okay. But when you reverse the direction of applied field, the direction of saturation polarization changes, but you attain saturation polarization once again. So there are two stable states which are switchable from one state to another one. So that is what is ferroelectricity all about, and polymers essentially exhibit PE hysteresis loops, which we draw between polling field and the polarization which we shall be talking of. And all ferroelectric materials, they are pyroelectric also. Okay. We shall be talking of what pyroelectricity is. Oh, yeah, it's there. Okay. Now, when we talked of change of polarization by change in mechanical dimensions or vice versa. By changing the dimension, that is by pressing a crystal or stretching a crystal, you have change of polarization. Or by changing the direction of electric field, you can have change in the dimension of the crystal. So piezoelectricity was reversible. So essential thing in all of them is the creation of dipole moment, as we talked about. Same way, you may have some changes in crystal structure depending on the temperature. Depending on the temperature, that means if the material already have a spontaneous polarization, and if the temperature is changed, then still there are chances that charges may appear on the surface. So in the piezoelectricity, charges appear on the surface of a material due to change in pressure, whether it is compression or tension. But in case of pyroelectricity, this polarization changes due to change in the temperature of the material, due to change in the temperature of the material, right? So that is a very essential thing. Of course, you can't measure the temperature here, but you can definitely measure the change in temperature. You change the temperature, polarization on the charges on the two surfaces, or the polarization will change. Essentially, basic चीज के पीछे सिर्फ again it is the same that there is a change of polarization, or there is a creation of non-centrosymmetricity with the change in temperature. Again, they need to positive and negative charges. They should not be coinciding. Essentially there has to be a dipole, two opposite charges, separated by distance. That happens. If that happens with temperature, then it is periodicity. And this is the one that is used for night vision devices, IR sensors, and all those, right? So IR imaging, it has been used. So this is the periodicity we talked of. This is a PE loop which we are talking of. Need not to explain the loop, but okay, you have a if you increase the field, the potential goes on increasing, and at beyond one point, correlation won't increase. So you have saturation correlation, you have remnant correlation, then you have coercive field in one direction, then the field direction reverses, the correlation attains saturation in the other direction, and then again the cycle repeats when the field is reduced. You again have a saturation correlation and remnant correlation on the other side with EC if the loop is symmetric. The value of EC and minus EC, they're supposed to be identical in case of symmetric loops. So this is one thing. Okay, as I was talking earlier, that when we talk of electroactive polymers, the polymers are essentially thought to be always non-conducting, but there are conducting polymers. Here are the names you have: polyester or polypyro, polythiophene, polyphenyl sulfide, and some of the polymers. They are even superconducting. PSN, poly phenyl sulfide is the one that is probably that's the one. Otherwise, we have polymers which are highly conducting. So here we were talking of the polymers which were like PVF, PVDF, PVC, polyamides, then polyacrylonitrile. So essential requirement for polymers to be ferroelectric polymers is that they should have dipole moment, right? So we shall be talking of cyanopolymers now. Okay, so the two polymers which we are going to talk of today are polystyrene acrylonitrile. So I briefly refer to it as SAN, SAN. Otherwise it is PSAN, but it is we simply refer in market we refer to it as SAN. Okay. Now this is one copolymer of PAN and polystyrene. Okay. PAN is polyacrylonitrile. Then you have polystyrene, so you make a copolymer. I'll tell you why copolymerization is done. And then we have a terpolymer where we have three components: polyacrylonitrile, butadiene, and styrene. So that is ABS. ABS terpolymer, and that's a copolymer. And actually, polyacrylonitrile. Okay, I shall be talking of it in detail here. So, essential feature of a cyanopolymer is that they have CN group. Okay, and so the polymers which have CN group in their polymer chains are something like polyacrylonitrile, which we call PAN, PVDCN, polyvinylidene cyanide. Then two I talk of SAN and ABS and polyacrylonitrile methyl acrylate. So these are different polymers that have cyanide groups in their polymer chains. Okay, and cyanide group is the one that have very high dipole moment. It is 3.5 dpi unit. Okay, so that value is much higher than what we have in polyvinylidene chloride, where it is around 1 point something 1.8 or 1.9 dpi unit. So in CN it is 3.5. So large piezoelectricity was expected in cyanopolymers. Okay, now look at the figure A. So C is slightly positive and N is delta negative. So you have a dipole here, and it is this dipole that gives rise to spontaneous correlation, and then it gives rise to all the ferroelectric based properties, piezo, pyro, or P loop, and other things. Okay. So now, if the dipole moment is so high, then why not to have it in polyacrylonitrile? Interestingly, this polyacrylonitrile have a helical structure. Okay, it's like DNA or RNA. It has a helical structure where CN group is tightly woven around with the chain. So this CN group is not able to move freely in polyacrylonitrile. So chains have a lot of mixing up, and CN group is not free to move. So polyacrylonitrile, though it have only CN group in its chain and nothing else, it does not have very good piezoelectric properties because mobility of CN group is not possible because of its chemical structure, chemical and physical structure. CN group is not mobile unless until dipole is able to move. You will not have any charges appearing on the surface of the film of pan. I tried a lot, but it never happened. Okay, so that's why we had to make it uh, copolymers. That's why a SAN, polyacrylonitrile or polyvinylidene cyanide and all those. Okay, so that's the reason. Though it has very high dipole moment, but CN dipole is not mobile enough in polyacrylonitrile PAN because it has a helical structure and it is not very tight structure. So opening up of that structure is simply not possible. So that's why you have to break up that chain into different by adding some copolymers, so that mobility of dipole, that CN dipole can be increased. And that's what we were able to do in case of SAN and ABS. Okay, other people did in case of polycyanide or polyvinylidene cyanide and so on and so forth. Okay. Now the material which we used that was SAN, and we had different samples of SAN which contained 28% of cyanide group and 72% of acrylonitrile group, and this all things were verified using FTIR. Okay, so these two peaks were height of these two peaks were measured, and then ultimately we were able to calculate that SAN 1 has 28% of cyanide, 72% this. So composition varied from 28 to 41%. And interestingly, uh, uh, we find that with increase in the cyanide composition, the glass transition temperature of the SAN it increases. So when the percentage is 28%, glass transition temperature is 108, and it became 113 for 41% composition of cyanide. So you see that same way pan has pretty high, still higher than this. Okay, so that is the essential thing we have because now this was checked through differential scanning calorimetric studies. So the peak was occurring at higher and higher temperature for the materials having higher compositions of cyanide. Now, this is the normal structure of a polymer. Polymer can have either there is one fringed mycelium model. This is a semi-crystalline polymer where you have straight chains. That is figure A I'm talking about. You have straight chains. Then you have some jumbling at the ends. So these are actually semi-crystalline polymers. So, but the chains are perfectly parallel to each other. That area has more crystallinity, right? So that's more crystalline. But at the chain ends, uh, it is uh, it is almost amorphous. It is just like a grain boundaries you have in other materials. Okay. Or it can have switchboard structure as shown in figure B. Okay, so you have single chains, and then you have loops at the ends coming at the different surfaces, at lower and upper surfaces. So you have different loops. Otherwise, you have folds of the polymer chains in major part. So that is a switchboard structure we talk of. Or polymers can have spherulites. Okay, that's lamellae we call. So that is like again like different grains. This also have these are different types of structures as seen from different studies, right? Okay. Now this is the interesting setup which we actually use to induce piezoelectricity say in piezo or pyro and ferroelectricity also in polymer, right? So this is a stretching and corona polling unit. Okay, okay. And here basically what we have a motor at the end here. This is the motor here, and we have two clamps. One is A and the one is say B. And this is a small heater. It is basically a aluminium block that has been hollowed from inside so that we can place a heater. So we place a heater here inside this. So polymer film is stretched over the surface of the heater and held together by the clamps. So polymer film is stretched between clamp A and clamp B, and its surface is touching the heater. It heats hot surface. Okay, and when this motor is moved, it so happens that clamp A and B, they move in the opposite directions. I hope you get me. When A and B are moving in opposite directions, then film will be stretched. Okay, when they are moving outward. So one is moving towards the motor, other is moving in the opposite direction. So film automatically gets stretched. Here again, you reverse the direction of the motor, you bring the clamps together near to the heater. You place a film on the heater, and again change the direction of the motor so that again these clamps A and B, they move apart. They move apart, thereby stretching the film they are holding. Okay, and so that's how that's how the film is stretched. Now that is only one part of the story. Here only the film has been stretched, right? So this is the stretching of the film. Now, what is the role of this unit? Now, this is a polling unit. This is a corona polling unit. We have a very sharp needle here, which is given around 10 kV, 10,000 volt DC. Okay, and then we have a grid here. So when this high field is developed here, and then this air gets ionized, okay, and you get a corona here, corona, that is a cloud of positive and negative ions. Air gets in fact ionized. There's such a high field. So this is given quite higher voltage, 8 kV, and this is a small grid. It is kept at around 2 or 3 millimeter apart from this surface. So this is a polymer film that has been stretched, and this is a grid where we don't apply more than 4 kV. Actually, that is the polling field we have, and corona is helping us in a way by ionizing the air and then creating a good field, uniform field over the surface of this. So actually, this is the magic device we have. Okay, so we have, again I repeat, we have this stretching and polling unit. We have two clamps moving in the opposite directions, holding the film. So thereby, when they move apart, they stretch the film, and the field is applied at the same time. So film is stretched and the polling is done. Field is applied. That is stretching and polling. Sometimes it is done simultaneously. It is simultaneously stretched and corona polling. Because what we feel here is when the film is made hot, when it is heated, temperatures are different for different materials, right? For sand, it was around 85 degrees centigrade. That was optimum temperature at which it had to be kept before pouring. It gave the best results. And for ABS, it was around 90 degrees centigrade. So that had optimization karni padti. Okay, so that always have to be done. Okay, and what we find here is when the film is hot, the dipoles are more mobile. Simple logic is that when the film is cold, and if you apply field across the film, a dipole, because the film is say cold at room temperature, dipoles will not be able to move much. But when the film is heated, the dipoles would be able to move because thermal energy will assist the motion of the dipole. They will get aligned in the direction of the field. And sometimes in some of the polymers, simultaneously
Right.
Simultaneously, stretching and corona pooling is done. That means film is stretched at the same time field is also applied, right? What happens with that is that when you stretch the film, the dipoles are already moving because of stretching, because of physical movement of the film. Okay, and at the same time field is applied, then that may also increase the polarization. And it has been found that simultaneously stretched and corona pole films were they give very good results in some of the polymers. Though for me, simultaneous stretching and corona poling didn't help much. It was only stretching and poling or poling, heating and poling that helped. Okay. But in case of polyvinyl chloride, there was a research scholar there who worked, and in that case, he was able to get results with the simultaneously stretching and corona poling. So it is like heating a cold film, heating a hot film, heating a stretched film, heating and poling a stretched film, or heating and poling, heating at the same time poling the corona pole. So these are the different things which we do. Okay, now this is what happens. Look here. Now this is a semi-crystalline polymer, and what we find here is here it is all jumbled up. So these are two clamps, and now when these two clamps move aside, all these polymer chains which are all mixed up and wrinkled here, right? They are all loops and loops. So they start opening up. So what happens with this is crystallinity increases. That is one thing. एक तो crystallinity बढ़ जाती है. दूसरा spacing between the chains that gets reduced, and hindrance to the movement of dipoles that get reduced. लेकिन बहुत ज़्यादा stress करेंगे, then you may have simply chains will simply fall apart like this. So that is the इससे तो electric breakdown ही material की जल्दी हो जाएगी if you reach stage 3 and 4. So stage 2 is the one that we find is the best to use here. But a reason you can see the stages here. Here the all loops are mixed up, so dipoles will definitely will not be able to move much if you apply field here. But when you stretch, the chains are unjumbled, they align parallel to each other, creating more space for the dipoles to move, and you get better polarization. Look, now this is what happens. This is unfold film in first case. So you have this is switchboard structure kind of thing. Say we have one grain kind of thing which have net dipole movement in this direction. So you have another part here where the dipole movements are pointing in the opposite direction. So there is self cancellation within the polymer, right? Though dipole movement is there is self cancellation. But when you do polling, you find that all these dipoles, net dipole movement, they try to move. ये खुलने लगते हैं and they try to align in the direction of the field. Here the field has been applied, and we find that all the dipoles are trying to align in the direction of the field. Okay, they are better aligned, I would say. They are not ideally aligned. Saturation polarization वाली condition तो नहीं है, but they are definitely better aligned in the direction of the field as compared to the first stage where it is unpoled film we have. So that is the effect of the polling. Okay, so domain orientation gets better along the field direction due to polling, right? So that is. So now this is the case here. Say if in first case, if you look at the figure A, that is a piezoelectric film, and say it has a lot of dipoles within, right? Here it has a lot of dipoles. Now when look here, now these dipoles are near to the surface, so we have some mirror charges developing on the surface, right? Mirror charges are developing on the surface. Here, since the dipoles positive ends of the dipole movement are on this side, so we have negative charges on the surface. These are again mirror charges. But now when you compress the crystal, now what happens? This dipole has also come nearer to this. Okay. Even this dipole has come near to the surface. This has also come closer. Or in other words, there is change in the charges here. Okay, ये surface charges जो हैं, they will change, and as a result, you will have development of some kind of some current will start flowing, right? Some current will start flowing because of the charges. If you close the circuit, the current will start flowing, right? And if say initial condition is this, you move these two upper and lower surface apart, then again there is change in polarization, again the current will flow, right? So this is the basic thing which we have. So this is the state of a polymer when it is, of course, it does have oriented dipoles in it. Dipoles are oriented, but they are not, since it is uncompressed state, we have only some charges near the surfaces. But when they are compressed, dipoles get nearer to the surface. More number of dipoles come closer to the outer faces, thereby changing the polarization and giving rise to opposite charges. Thereby, a piezoelectric current starts flowing in a circuit that if it's closed. Now, this is the piezoelectric coefficient which we get for cyanopolymers. For example, for PAN, it is 0.3. Reason I have already explained, because the structure is helical one and the CN dipole isn't able to move. PVDCN, polyvinylidene cyanide vinyl acetate. It is a copolymer. It has the best piezoelectric coefficient. It is around 10 picocoulomb per newton. The material which I worked on initially had 1 picocoulomb per newton, but with the help of stretching and chronopolling, we were able to increase it to around 4.5 or 5 picocoulomb per newton. So we increased the value by 5 times. So that was the improvement. Okay. Otherwise, PAN, polyacrylonitrile methaacrylate. So that has a piezoelectric coefficient of 3, and this has 2.2. Polycyanoaryl ether, it has again D31 of 3 picocoulomb per newton. Now, what this D31 and what is 3 and 1? What does these indicate? So basically, these are look here. Now, this is a film that is stretched 1. This stretching direction is labeled as 1, right? This direction is labeled as 1, and if the field is applied perpendicular to the stretching direction, so that is 3, right? That means in this case, when we measure the piezoelectric coefficient, not only during polling, otherwise when we measure the piezoelectric coefficient, we stretch the film in direction 1 along the length, along the direction 1, and we measure the charges along this direction 3. जो surface charges change होते हैं, जो piezoelectric current flow करता है, so that is measured around direction 3. Okay, so that's why D31. Okay, that's 1. Okay, then we can have even D33. उसमें charges भी इसी field इसी face पे measure करते हैं, और जो चीज drop करनी होती है इसके ऊपर, वो भी इसी surface पे ही drop करते हैं. But when we are measuring D31, the sample is cut in such a way that film is stretched in this direction, and change of charge move is measured along 3 directions. And perpendicular to stretching direction, we have the direction 2. So this is direction 1, this is direction 3, and this is direction 2. And if it is twisted, if you twist the film, then you may get other axes, like you may have axis 4, you may have axis 5 and 6. But for us, directions 3, 1, and 2, these are the ones that are important, right? Okay. Now this is the setup that was used to measure the piezoelectric coefficient. Now here we have the film that is stretched. Now this is the polymer film that has been stretched, that has been held with the 2 clamps, plastic clamps, and here we have a hook. So when we place a weight here, the film gets stretched. When this film gets stretched, what will happen? There will be a piezoelectric current flowing in the circuit. So from where that is further through electrometer that is recorded on XY recorder. From there we are able to measure the piezoelectric coefficient. So what I am saying is the film during measurement of piezoelectric D31, the film is stressed around the direction 1, along the direction it is stressed in, right? And the charges are measured on the other two faces. So that's why the D31, and this is the formula that we use. Say Q is the charge that develops on the surface that can be calculated. A is the area of the electrode. T is the thickness of the film. W is the width of the film. F is equal to m into g. That is the weight you suspend and move here. इसमें थोड़ा सा weight हम लोग डालते हैं. We drop the weight along the hook. Then we pick up. Again we drop the weight. Again we pick up. So we find this kind of recording on the X-ray recorder. From there, D31 can very well be calculated. So this is also called linear piezoelectric coefficient, or sometimes called tensile piezoelectric coefficient. Now, in case of polystyrene acrylonitrile, yes, there's one more thing. Okay, in addition to stretching, sometimes annealing is also done, because we prepare the films with the solvent cast method. So we try to anneal the films. And best annealing temperature is 85. Okay, and that is the temperature at which all films are annealed. Because by annealing, what happens is any residual solvent in the film that gets vaporized, number one, and then if some stress is created within the film while it's removing the film from the glass substrate. Okay, so all these things can be taken care of. So when you anneal a film, small stresses and strains that develops within the film while it is being handled, so they get removed. Extra solvent gets removed. So overall, what we say is Christianity improves. Okay. Now, in case of unstretched styrene acrylonitrile film, we find that when the annealing temperature was around 85 or 90, 85, we find that piezoelectric coefficient was maximum. So for unstressed coronapole film, piezoelectric coefficient was only, say, look here, around 1 picocoulomb per Newton. Okay, but when the film was stressed, we find that we got the maximum piezoelectric coefficient of around 4. Sometimes we got 4.2, in some cases we got 4.5, but we never touched, we never went around more than 4.5 in fact, or around 5 for vinegar. So there was 4 times improvement in piezoelectric coefficient, look here. Okay, and when, as I told you, when stretching ratio is big, what happens? The chances of breakdown, electric breakdown of the film, that increases. Okay, जैसे आपने पिक्चर में देखा, उसमें देखा होगा कि when chains are moving apart, then the chances of electric breakdown increases. So stretching the film to a very high ratio is damaging for the film. But stretching ratio of 2.5 times, and that is initially if 1 centimeter long film is there, it is stretched to 2.5 times. It is made 2.5 centimeters. So that is a stretching. But stretching ratio beyond 2.5 seems to affect D31 adversely. Okay. Now this is with the Pauling field. This is the variation of piezoelectric coefficient with the Pauling field. So the Pauling field applied was found to be, best Pauling field was 45 MV by meter, megawatt per meter for the film, right? And beyond that, if the field is applied, then there is again electric breakdown starts, and piezoelectric coefficient that starts falling. In fact. So you get the maximum value of D31 when the Pauling field is around 45 MV per meter. So look here, now with the increase in the Pauling field, we are increasing the polarization. And that is one essential feature of dipolar polarization. That is, polarization should increase with the Pauling field linearly. Okay, so this is almost, look here, the type of curve we have. because of the increase in polarization in the uh, despite the fact that it is unstressed film, still we find that D31 increases and becomes maximum at 45 MB per meter, and beyond that there was electric breakdown in the film and D31 decreased. Now for look here, now it is again for this is for stressed styrene acrylonitrile film. The maximum value obtained is around 4, 4.2, 4.3. So there was a variation always. So that's why we had to plot it like this. So we find that at around 50 MV per meter, slightly less than 50 MV, 45 or 48, this D31 became maximum for a stretched styrene acrylonitrile film. Please remember here, the film had been annealed at 80 degrees centigrade for 15 minutes, and it was tested to a ratio of 2.5, right? So other factors have to be kept constant if you are measuring, if you are varying one field, one particular thing. If you are measuring polling field here, if you're looking at the variation of DC1 with the polling field, so other parameters will have to be kept at optimum values. Okay, so that's how things are done. Now this is a thermally stimulated current studies in case of stressed styrene acrylonitrile films. Now look here. Here, thermally stimulated current studies have been done, and cold films are subjected to thermally stimulated current studies. And when the temperature is raised, what we find that all the films, they show peak at this particular temperature, okay, at around 90 degrees centigrade, 95 degrees centigrade. Then there was another peak at around 102, 103. So that corresponded to basically the glass transition temperature, and this corresponded to the temperature at which the maximum polarization had been obtained, and that temperature had to be kept, right? So this is at the different polling fields we did. Okay, that was for thermally stimulated current studies. Now, why these studies? Because we can find out the polarization in the film under different conditions by TSC. Because by D31, by measurement of piezoelectric coefficient D31, the active polarization cannot be measured. So polarization can be measured by two ways. One is by calculating the area under the TSC thermally stimulated current studies, these curves, or by hysteresis studies, right? And the value should come out to be equal, and it's a linear dependence on polling field and other things that can only be studied here. So this is what actually we found. Okay, from TSC we were able to calculate PR, that is polarization, and it was found that this polarization completely varied linearly with the polling field. Look here, right? So these are linear dependence of polarization with the polling field that corroborates that whatever piezoelectricity or pyro or ferroelectricity which we are having in corona pole films, it is mainly due to dipolar. It is only in fact due to dipolar polarization. Okay, not ionic or electronic or space charge polarization. So it is due to dipolar. So essential feature of a dipolar polarization is that polarization has to be proportional to the polling field. Okay. So D31, this is in case of the other polymer we were talking of, that is acrylonitrile butadiene styrene. We find that again polling field, that D31 increases with the polling field. In fact, nobody else had studied ABS earlier. Okay, so we were the first people to study, and we were able to get up to 2 picocoulomb per Newton. So the results were not very promising. So we didn't do much higher studies in that, but yes, we did study this cyanopolymer as well. So where DC1 was studied. Okay, so this is in case of unstressed, probably graph is repeated. This is the polling temperature. Now, why with the polling temperature D31 is more? Because more the polling temperature is the temperature of the film, temperature at which the film is kept while it is being subjected to electric field. Okay, so that is the polling temperature. Higher the polling temperature, okay, more would be the mobility of the dipoles. There would be better chances of the dipoles getting oriented in the field direction. And that's why with the increase in the polling temperature, D31 improves because ultimately it is directly linked with the polarization. But when the polling temperature is increased too high, then again dielectric breakdown starts. Okay, thereby reducing D31. So 85 degree centigrade temperature was found to be best polling temperature for styrene acrylonitrile, right? So this is again at the same peak you have it for stressed styrene acrylonitrile. Here you had it for unstressed styrene acrylonitrile. The peak is at the same temperature, but the values of D31 obtained are different. Here they are around 1 picocoulomb per Newton in case of unstressed films, but for stressed films it is around 4 picocoulomb per Newton. So that is the beauty of things that we were able to improve the result. At least safely we can say up to 4 times. Okay. So now look here, the effect of stretching ratio on the piezoelectric coefficient D31. So look here. So it was when the film was unstretched, it was only 0.2 picocoulomb per Newton. But that is for unstretched film I'm talking of. So with up to 2.5, we were. This is in case of ABS. Sorry, this is in case of ABS. What I thought this actually is a 4 picocoulomb per Newton. So here it is at 2.5, it became 1 picocoulomb per Newton. That means for ABS, we were able to stretch the film up to 4 and get maximum value of piezoelectric coefficient up to 1.75. Whereas in case of styrene acrylonitrile, the best stretching ratio was 2.5 with a value of 4 picocoulomb per Newton here, right? So that is in case of ABS, earlier results were in case of styrene acrylonitrile. Now, the polling temperature, the best polling temperature for ABS was 90 degrees centigrade, whether it was, whereas it was 85 for sand, 90 for ABS, right? Okay. So that was one kind of piezoelectric coefficient. But now we have another type of piezoelectric coefficient, that is bending piezoelectric coefficient. Look at the all these. Let me tell you, all these apparatus were fabricated in the lab. Okay, whether we did the DC1 measurement, simultaneously stretching and corona polling unit, DC1 measurement, beta 33 है this is something wrong here. Beta 331, yeah, here it is. Beta 331, whether it is this measurement, all the apparatus were fabricated in the lab. Now here we have, in fact, here what we have here. Here we have a micrometer. Here is the polymer film with the two metal electrodes on the two opposite sides, this surface and the other surface. This is the polymer film, which is connected to electrometer. We use the Keithley electrometer there. And then film is held clamped at this place. But this end of the film is free. This end of the film is free. Here T is the thickness of the film. Okay. Delta Z is the deflection which we are able to produce with the help of the micrometer. When you rotate this micrometer, when it moves in the forward direction, the film bends. And by bending, we can find that still you'll get piezoelectric current moving in the electrometer, and we are able to calculate the bending piezoelectric coefficient. Whereas this is the dielectric constant of the material, this is voltage that you get here when this film is deflected. Delta Z is the deflection, and T is the thickness, and K is some constant for this particular setup. Okay, so this is the apparatus which we use for measuring bending piezoelectric coefficient. Okay, now this is the case. Now this is the in case of styrene acrylonitrile. And now first curve is for unpooled films. Look here, even unpooling of films, unpooled films do have some kind of, they show bending piezoelectricity. Now this is pooled films, but not stretched. These are stretched and pooled films. So we find that deflection, the voltage developed by bending was maximum for for the stretched and chronopole films. We have three curves here for unpooled films, for pooled but unstretched films, and C, stretched and chronopole films. So best results were obtained in the stretched and chronopole films. Okay, and this is correlation between D31 and beta 331. Okay, where the polling temperature had been kept different, right? So this is what we get. They all points. They almost linear relationship between the two, right? If D31 is affected, beta CG1 is affected too. That is the simple thing we have. Now this is in case of ABS. Okay, with the polling field, we have the variation of D31 concept. Okay. Yeah, this is the one. This is the, we have it for voltage V3 in case of unstretched, unpooled, and stretched and pooled ABS films. This is the voltage we get, and use the formula that was already given. We find that this is the kind of variation we have, and beta 3 will be get. Okay. One thing which was very essential to explain was that we used X-ray diffraction method to obtain the crystallinity in the styrene acrylonitrile and ABS films. Okay, XRD was done, and this was the method used. This is called Hinrichsen's method. Okay, where bigger polymers don't give you very sharp peaks. The peaks are very broad. This is in case of not SAN or ABS. It is in case of polyacrylonitrile. So we find that this is one very broad peak. Then there is another broad peak. That means you have crystallites of different sizes basically. Okay, so this AC represents the area under these peaks, and AA represents area under the amorphous region. So this area, total AC by AC plus A, total area under the peak, uh, that is under the amorphous region plus a crystalline region. So that gives you area under the crystalline region versus the total area under the two peaks. That gives you percentage of crystallinity. Interestingly, even crystallinity affects the D31 and TSC studies. Okay, so this is the crystallinity that improved just by 3%, not much. So for unannealed, unstretched, unpooled films, in case of SAN, crystallinity was 24. Then it increased to, by annealing, it increased by at the 2%. Stretched and unpooled, it went to 27%. So that's what. And in case of ABS, we find that annealing and stretching increases the crystallinity in a big way. So for unannealed, unpooled films, it was 29, whereas it went up by another 9%, right? So it went to 38% in case of ABS. Okay. So this is piezoelectric coefficient with the different acrylonitrile compositions. As I told you, have more of acrylonitrile composition, more the loops in the film, and more the difficulty for cyanide group to move. So dipoles aren't able to move with the higher compositions of acrylonitrile, right? So 28% appear to be best now for us. Now this is the Sawyer and Tower circuit which we use for P. This is not D. This is actually PE hysteresis loops. Okay. And look here. As I was explaining that whenever a material is ferroelectric, then there has to be cooperative behavior of the dipole that has to be there. Okay. And polarization is, of course, it depends on the density of dipoles. It depends on the dipole moment. It depends on the Pauling field. Okay. It depends on the Pauling temperature, Boltzmann constant, dielectric constant, other things. And look here. First thing is polarization is proportional to the Pauling field. That is something very essential. वो जो हमने TSE studies से भी prove कर लिया, and we prove through piezoelectric studies as well, right? But the essential thing is that on we already have these values. We have these values also. These are all given here. Okay, and we found out the value of G. Okay, and if at all the material gives a cooperative behavior of the dipoles, then G should be greater than 1. Then only you are going to get what you call hysteresis loop. Otherwise, hysteresis loop nahi aayegi, right? So there has to be a cooperative binding between the dipole, adjacent dipoles. Then only you are going to get hysteresis. Then only the material is said to have some kind of spontaneous polarization, which is already there. Okay. So, so we have Pauling fields. G was found to be around 1.3. Look here. So this showed that the value of G in excess of unity implies that some cooperative dipole motion of dipoles is there in the field. Now this was established through TSE studies. Okay, we knew N, we knew dipole moment, we knew the Pauling field, we knew the dielectric constant and low and infinite, very high frequencies. And putting in all those, we knew K, we knew TP, we knew the value of PR as we obtained from TSE studies. We found that G was found to be equal to 1.3 in case of unstressed film, sand films, and it was around 2, and it was around 2 for stressed and chronopole films. So the values of G higher than 1 indicates that there was a cooperative motion, cooperative dipole motion within these films, within these sand and ABS films. So that was that. Now this question was given by Frolic. This is what we used to find out whether cooperative motion of dipoles is occurring or not. Okay, so we were able to find these kinds of loops here. Here, these are the loops that are at different temperatures. Okay, so and these are the values of remanent polarization at different Pauling fields. Okay, so again, we are finding that behavior is almost linear kind of. Yes, there are some points here and there. If you consider 1, 2, 3, 4, 5 points out of 7 or 8, we find that polarization is proportional to the Pauling field. So that is once again we are trying to prove that whatever polarization of piezoelectricity or ferroelectricity we have in these films is due to dipoles, not due to any other. Because a dipole, in case of dipole polarization, polarization has to be proportional to E, right? So this is what we had from here. And another thing, this hysteresis loop was studied at different temperatures. Okay, and we find that this loop starts vanishing when the temperature is increased. Okay, so when this coercive field was measured at different, when the loop was down at different temperatures, with slightly heating it, we find that this kind of variation, and there's a fall in ECs. There's sudden collapse of the PE loop at higher temperatures near to the glass transition temperatures of the film. Okay, it is there's a sharp fall at around 100, 105. That indicates, so fall starts at around 90 and so it's all over by 110. So that means here randomization of dipoles is taking place, and that polarization is all lost. And this is what is actually expected from a film that is having only dipoles, right? So So this is another corroboration of the fact that we have dipolar polarization in the film, and the dipoles have cooperative motion. Okay, this is PE loop for cold sand films. From there, we have found out PR. Okay, and the value of PR obtained from TSE studies is slightly less than what we get from PE loops. This is what we have. So this was actually the setup used for studying pyroelectric studies as well as thermally stimulated current studies. I'll just explain what these are. Here again, we have this is a base, this is a heater embedded in it. So we have two thermocouples, TC1, TC2, measuring the temperature of heater and that of the lower electrode. Sample is placed here, upper electrode is placed here. In fact, we use brass electrodes here. So this was brass, and okay, of course, aluminum electrodes were coated on the films, but they were placed between. This was a brass substrate, and sample was placed here, and then the electrode here. So when you heat the film here, because of the motion of dipoles within the film, there is change the surface charge and there is a flow of current in the circuit. So that can you can use that for thermally stimulated current studies. You can also use the same setup for pyroelectric studies. Now this is a pyroelectric thing which we measured. Okay, actually this is pyroelectric coefficient P, where I is the pyroelectric current that flows in the circuit, beta is the constant heating rate, and A is the area of the electrode which you have to find, and then you can find that you have pyroelectric coefficient for unstressed sand film. It's around maximum value is 0.8 nanocoulomb per centimeter square Kelvin, whereas it is almost double, more than double. It is around 1.6, more than 1.6 for stretched and chronopole film. So pyroelectric coefficient is higher for stretched and chronopole film as compared to the other film that is unstressed and chronopole film, right? So this is in case of ABS, right? They are showing similar results, A and B both. Whether they are stretched or unstretched, they are showing similar results. But this is what we have. Okay. Now this was about cyanopolymers which we talked of, and this PVDF is the one that is mainly researched upon, and it exists in different phases, alpha and gamma phases at different places. But since this material has been studied a lot, but in our lab these days we are studying PVDF and BCZT films. We are using two ways of preparing the films. One is melt press technique, and there is solvent cast technique. And we are trying to compare which one of these two gives us the best results. Okay, so this is still under study. So this is a melt press method we have. We have PVDF, and we are using PVDF as a matrix basically, and we use BCZT nanoparticles which are spread in PVDF matrix. So after grinding them, they are put here in this melt press film, where we have metal foils on two sides, and we press the film. We heat the film and then we press. Basic unit is kBr, hot press machine. Okay. So similar thing we also tried in sand, but we are trying on this composite polymer BCZT nanoparticle this time. This is one technique which we use. Here, melt press, the powder is heated so that it melts easily, and thereafter mechanical pressure is applied so as to get a film. So we are able to get composite films. The easy method is to produce solvent cast methods. So in this case, we are using DMF solvent in which PVDF dissolves, and the BCZT nanoparticles are spread in the solvent. So you get a kind of suspension, right? And then you can spread it over a substrate and put that in a vacuum oven. so that slowly the solvent evaporates, leaving behind a film. But for styrene hydronitrile, we used acetone for solvent cast films. So that was just to give you an idea that lately we are working on these things. This is for PVDF film, milk press, and solution cast. Okay. EC is found to be same. PR is slightly more in case of milk press films. So still we are working on it, right? Yeah. Okay. Actually, we are trying to study this energy storage. We are trying to study this PVDF BCZT composite films for energy storage devices. We are trying to. This is just a part of the history loop you see here. From here, we can find out the energy loss density and while charging and while recharging of the film. So you know the recoverable energy density and the area under the loop. By comparing, you are able to find out other parameters. So this is the thing which we are just reported in a research paper. Now coming to the applications of these films. Okay. Now they have huge number of applications. I'll just elaborate one. So this is one which we where we were in fact in our lab at Roorkee, we were able to make this microphone here in the lab itself. Though this picture is not of that microphone, but we were able to prepare. Here you can see that this is a polymer film we have. Okay, so here we have a substrate, and there is an air gap between the polymer film and the lower electrode. So you have upper electrode, you have lower electrode, you have a small air gap between those two electrodes. Okay, when you speak, this is actually a microphone. When you speak, this polymer film actually moves. When it moves, there is the insulating air in between. That gap slightly varies; it changes, right? So this microphone is able to work because you can, if there is a change in capacitance, you are able to, that is giving rise due to the change in charge, and then you have a flow of current outside. So people have been working on it, and it has been used for, especially PVDF. It has been used to make microphones, color microphones, miniature microphones, and a huge number of applications. Just to name a few, I have a few here. Electromechanical applications. These have been used for making of speakers, tweeters, headphones, ultrasonic transmitters, hydrophones, keypads, okay, light reflectors, telephone dials. So all these have been, these are the applications, electromechanical applications. Okay. And then we have mechano-electrical applications like microphones, accelerators, point sensors, impact detectors, where mechanical energy is converted to electrical energy. That's why the names are different. Here, electrical energy converted to mechanical energy. So we have electromechanical sensors. These are all mechano-electric sensors, right? So that's one thing. Then, as I told you earlier, pyroelectric sensors we make, which are used for IR detection, then for radiometer, photocopiers. So these are all pyroelectric applications. Then we have electro-optical applications for, as we were talking of, this optical frequency shifter and jacket optical fibers and other things. Then, yes, interestingly, they have been used hugely in biomedical applications. Okay, I read about one application where a polymer film was placed between the ribs of a person. Okay, it was placed between the ribs of the person. Now, as we inhale air and exhale air, when we inhale the air, the distance between the ribs increases, thereby stretching the film. Okay, when we exhale, when we throw the air out, the distance between the ribs, it actually decreases. So alternately, you are stretching the film and again loosening the film, again stretching the film and loosening the film. So that was used to operate insulin pump in a material, in a person, right? So energy didn't, so cell, so they didn't have to apply any put any cell there to get some voltage that was available from that film itself. Okay, especially PVDF and PVDC, and they have found huge applications. Even we read about an application where a bone had a hairline fracture, microfracture, right? And if you place a corona charged film, old film, I would say, corona charged film on that joint, uh, thereby enclosing that hairline joint, it enhances the growth rate. Okay, because the film is charged, it is able to attract the calcium ions, other things that make up the bone, right? And so the healing process gets becomes very fast. So that is another application. And there at our lab, we were in fact working on a artificial heart also, because a heart is nothing but it is a pump. It contracts, expands, right? So if you can make a cavity of similar kind, and if you can really manage the cycle in such a way, then definitely you should be able to. So that was the idea we were working on, right? So that was, I'm talking of Penn State area, and we were working on relaxer polymers there. Okay. So we have huge number of applications in biomedical area and other areas too, and also on ships, because when ships remain underwater, the portion of the ship that remain underwater, that is that develops a kind of fungus, growth of fungus and bacteria that takes place. So that ultimately leads to corrosion of the surface. Sometimes these kind of vibrating films, though they are not vibrating in that sense, so vibrations are very small, right? But those vibrating surfaces don't allow the fungus to grow on the surfaces. It has been found that the life of ship hulls have improved when they use these kind of coating over the surfaces of those surfaces that were exposed to water. So, and you have tactile sensors, respiratory sensors I was talking of, and then micro manipulators and other applications. So this area is open for the researchers. I think they can do. Why I chose to speak on this was, this is something which you can fabricate within the lab. Okay, ये सारा चीजें लैब में फैब्रिकेट की जा सकती हैं. In fact, we also put up a patent there for the stretching and proton pulling unit when I left Turkey. I don't know whether they got it or not, but yes, we were working on these areas. Okay, thank you so much. This is all from my side. Thank you. Yeah.
Thank you so much, sir. Dear participants, now talk is open for the discussion.
Yeah, should you have any questions, I'll be glad to answer you. I don't know whether it is it's clear to all, or it is just plain. There's a difference between things being clear and the slate being clean. Yeah. Any questions from any audience?
If no questions, let's formally thank our speaker and simultaneously head of our department, Dr. Jasbir Hundal. So, Suman, it's to you. Please formally thank sir.
Thank you, sir. Thank you for this wonderful and informative session.
Yeah, you can collect the questions. If they have any queries or questions, just ask them to send a message or email to us, so that we should be able to respond to them satisfactorily. Yeah.
Dear participants, if you are having any question, you can type in the chat box.
Yeah, thank you very much. Some people are, yeah, seem to be responding slowly. Was I audible throughout? I mean, yeah, are they getting across the people? Thank you, Ganesh Kumarji. Thank you so much, Ganesh. Thank you. Yeah. Okay. चलो ठीक है सुना yeah. Kindly collect questions if you have any queries, any questions. I'll be glad to answer.
Questions. Anybody have queries? We will collect these questions and convey to you.
Now, we are going to provide you the email ID of all the resource persons. You may directly contact them. In case you have any query, you can directly contact them. Just very soon, I'm going to send you a file having the email IDs of all the resource persons who give talk or going to give talk in this FDP. Thank you all. Suman.
Thank you, sir, for such
Yeah,
wonderful
thank
and
you.
informative talk on piezo, pyro, and ferroelectricity of polymers. Thank you so much, sir.
Just let me type the message here. Thank you, everybody. Thank you so much. Thank you so much. Yeah.
So, dear participants, we will be here for ATAL FDP tomorrow at sharp 9:30.
So have a nice day. Tomorrow we will meet again at 9:30. Dr. Praveen Kumar from IUAC will be with us. Thank you very much for being with us. Thanks for being patient listener and have a nice day. See you again.
Thank you.